Saturn, the ringed giant, reigns supreme with its dazzling retinue of moons. Each moon, a celestial dancer, pirouettes around the gas giant. They vary in size, shape, and composition. Some moons gleam brightly, reflecting sunlight like celestial mirrors. Others lurk in the shadows, their surfaces scarred and ancient. These moons whisper tales of the early solar system. They hold clues to the formation of planets and the intricate dance of gravity. Scientists study these moons to unravel the mysteries of our cosmic neighborhood. Among Saturn's many moons, one stands out as particularly enigmatic: Phoebe. Phoebe is an outlier, a lone wolf in the Cosmic Ballet. Discovered in 1899 by William Henry Pickering, Phoebe immediately captivated astronomers. Unlike most of Saturn's moons, Phoebe's orbit is retrograde. This means it orbits in the opposite direction to Saturn's rotation. Phoebe's surface is a tapestry woven with ancient impacts. It's one of the darkest objects in our solar system, reflecting very little sunlight. Its unusual characteristics hint at a past shrouded in mystery. This tiny moon might hold the key to understanding the early solar system's chaotic beginnings. Let's delve deeper into the secrets of this captivating celestial body. The year was 1899. William Henry Pickering, an American astronomer, was meticulously examining photographic plates taken at a new observatory in Arequipa, Peru. The observatory, perched high in the Andes Mountains, offered exceptional views of the night sky. Pickering was searching for faint objects that might have eluded previous observations. Little did he know, he was about to stumble upon a celestial treasure. On August 16th, a tiny speck of light on one of the plates caught his attention. This faint object, barely discernible against the backdrop of stars, would later be known as Phoebe. Pickering's discovery was a testament to the burgeoning power of astrophotography. In the late 19th century, photography was revolutionizing astronomy. Astronomers could now capture images of the night sky with unprecedented sensitivity and detail. Photographic plates, coated with light-sensitive emulsions, could record the faintest whispers of light from distant objects. Pickering used a technique called blink comparison. He rapidly switched between two images of the same region of the sky taken at different times. Objects that moved, like planets and asteroids, would appear to jump back and forth. The tiny speck of light on Pickering's plates was moving, but not in the way he expected. Its orbit was unlike any other moon observed around Saturn. It moved in the opposite direction to Saturn's rotation, a phenomenon known as retrograde motion. This discovery immediately set Phoebe apart from Saturn's other moons. It hinted at a past far more complex and intriguing than initially imagined. Phoebe's retrograde orbit suggested that it might not have formed alongside Saturn. Could it be a captured object, ensnared by Saturn's gravity long ago? Phoebe is a small moon, a mere speck compared to the colossal size of Saturn. It measures approximately 213 kilometers, or 132 miles in diameter, roughly equivalent to the width of a small country. To put that into perspective, if Phoebe were placed on Earth, it would barely cover the distance between New York City and Boston. Despite its diminutive size, Phoebe packs a surprising amount of mass. Its density suggests that it's primarily composed of ice, mixed with a significant fraction of rocky material. This composition is similar to that of other objects found in the outer regions of the solar system, hinting at Phoebe's ancient origins. One of Phoebe's most striking features is its exceptionally dark surface. It reflects only about 6% of the sunlight that falls on it, making it one of the least reflective objects in the solar system. This darkness is attributed to the presence of complex organic molecules, similar to those found in primitive meteorites. The surface of Phoebe is also remarkably red. This reddish hue suggests that its surface ice has been chemically altered over billions of years by exposure to solar radiation and micrometeoroid impacts. These processes have created a layer of reddish dust and organic compounds, blanketing the Moon in a dark, rusty patina. Phoebe's surface is a testament to its long and violent history. It's heavily cratered, pockmarked by countless impacts from asteroids and comets over billions of years. These craters range in size from small, bowl-shaped depressions to vast impact basins spanning tens of kilometers. The largest impact basin on Phoebe, named Jason, measures about 101 kilometers in diameter. This massive crater dominates one hemisphere of the Moon, a stark reminder of the chaotic conditions that prevailed in the early solar system. The density and distribution of craters on Phoebe's surface suggests that it has remained relatively unchanged for billions of years, preserving a record of the early solar system's bombardment. Phoebe's combination of physical characteristics, its small size, dark and reddish surface, heavily cratered terrain, and icy composition, sets it apart from Saturn's other regular moons. Its retrograde orbit further reinforces its uniqueness, suggesting a different origin story. While Saturn's other major moons likely formed from a disk of gas and dust that once surrounded the young planet, Phoebe's characteristics suggest a different birthplace. Its composition and orbit point to an origin in the distant Kuiper belt, a region beyond Neptune populated by icy remnants from the early solar system. Phoebe's orbit is a celestial anomaly, a stark contrast to the well-behaved orbits of Saturn's other major moons. Most of Saturn's moons orbit in the same direction as the planet's rotation, a prograde orbit. Phoebe, however, defies this norm, tracing a path that's opposite to Saturn's spin, a retrograde orbit. This retrograde motion is a crucial clue to Phoebe's origins, suggesting a past far different from its neighboring moons. While the other major moons likely formed alongside Saturn, Phoebe's rebellious path hints at a capture scenario. It's like a lone wolf that strayed too close to a pack and got caught in its gravitational pull. Phoebe's orbit is not only retrograde but also highly elliptical, meaning its path around Saturn is more oval-shaped than circular. At its farthest point, Phoebe ventures as far as 12.9 million kilometers or 8 million miles from Saturn. This immense distance, more than 20 times the distance between Earth and the Moon, places Phoebe in a lonely region of space. As Phoebe journeys closer to Saturn, its speed increases due to the stronger gravitational pull. At its closest approach, Phoebe comes within 1.3 million kilometers or 800,000 miles of Saturn. This gravitational dance between Phoebe and Saturn is a delicate balance, a testament to the invisible forces that govern our universe. Phoebe's retrograde and highly elliptical orbit strongly suggests that it did not originate in the Saturnian system. Instead, astronomers believe that Phoebe is a captured object, a celestial wanderer from the distant reaches of the solar system. Its most likely birthplace is the Kuiper belt, a vast region beyond Neptune populated by icy remnants from the early solar system. These icy bodies, leftovers from the planet-forming era, are often perturbed from their orbits by gravitational interactions. Some are flung out of the solar system, while others are captured by the gravity of planets like Saturn. Phoebe's capture by Saturn was a momentous event, forever altering its destiny. Frozen in time, Phoebe serves as a cosmic time capsule, preserving clues about the conditions in the early solar system. Its composition, surface features, and orbital characteristics provide invaluable insights into the formation and evolution of the outer solar system. By studying Phoebe, astronomers aim to unravel the mysteries of the Kuiper belt, the processes that shaped the outer solar system, and the complex interplay of gravity that can capture objects from afar. Phoebe's story is a reminder that our solar system is a dynamic and ever-changing place, where even the smallest celestial bodies can hold profound secrets about our cosmic origins. Phoebe is a celestial time capsule, a relic from the early solar system preserved by the cold vacuum of space. Its ancient surface, scarred by billions of years of impacts, holds clues to the conditions that prevailed during the solar system's tumultuous infancy. By studying Phoebe's crater distribution and composition, astronomers can piece together the history of bombardment in the outer solar system. Phoebe's dark, reddish surface tells a tale of cosmic weathering. The interaction of sunlight, micrometeoroid impacts, and organic molecules has created a complex tapestry of colors and textures. Analyzing these surface features helps scientists understand the chemical processes that have shaped Phoebe over billions of years. This, in turn, sheds light on the evolution of other icy bodies in the outer solar system. Phoebe's composition is a puzzle, a mixture of ice and rock that differs from most of Saturn's other moons. This unusual makeup points to an origin in the distant Kuiper belt, a region beyond Neptune populated by icy remnants from the early solar system. Phoebe's capture by Saturn provides a unique opportunity to study a Kuiper belt object up close. The presence of water ice on Phoebe is particularly intriguing. Water is essential for life as we know it, and its presence on Phoebe suggests that the building blocks of life may be more widespread in the solar system than previously thought. Furthermore, the detection of carbon dioxide and other organic molecules on Phoebe hints at the possibility of prebiotic chemistry, the chemical reactions that precede the origin of life. Phoebe's journey from the Kuiper belt to its current orbit around Saturn is a story of gravitational encounters and cosmic billiards. Its capture by Saturn provides valuable clues about the dynamics of the early solar system and the processes that shape the distribution of objects in the Kuiper belt. By studying Phoebe's orbit and composition, astronomers can test models of planetary migration and the formation of the giant planets. Phoebe's story is a reminder that our solar system is not a static place, but a dynamic and evolving system shaped by the interplay of gravity over billions of years. Understanding these processes is crucial for unraveling the history of our own planet and the conditions that led to the emergence of life. Phoebe may be a small moon, but its influence extends far beyond its diminutive size. Despite its modest dimensions, Phoebe has a significant impact on its cosmic neighborhood. Its gravitational pull sculpts Saturn's faint Phoebe ring, a remarkable feature in the vastness of space. This ring is a tenuous disk of dust and ice particles that stretches far beyond the planet's main ring system, creating a delicate yet expansive structure. This ring, discovered in 2009 by the Spitzer Space Telescope, has provided astronomers with new insights into the dynamics of Saturn's rings. It is a testament to Phoebe's ongoing influence on its surroundings, showing how even small moons can have a big impact. Phoebe's dark surface material is also constantly escaping into space, adding to the complexity of its environment. This material forms a tenuous trail of dust that follows the moon in its orbit, creating a visible path in the cosmos. This dust, bombarded by sunlight and Saturn's magnetic field, undergoes constant changes, adding to the dynamic nature of the space around Phoebe. These interactions create a complex and dynamic environment, rich with scientific opportunities. Studying this environment provides insights into the interactions between planetary rings, moons, and the space environment, helping us understand the broader mechanics of our solar system. Phoebe's story is a reminder that even the smallest celestial bodies can play a significant role in shaping our solar system, influencing both their immediate surroundings and the larger cosmic landscape. In the annals of space exploration, the Cassini-Huygens mission stands as a towering achievement. Launched in 1997, this ambitious mission spent 13 years exploring Saturn, its rings, and its retinue of moons. Among its many targets was the enigmatic Phoebe, a moon that had captivated astronomers for over a century. On June 11, 2004, as Cassini journeyed towards its rendezvous with Saturn, it flew within a mere 2,068 kilometers, or 1,285 miles, of Phoebe's surface. This close encounter, a cosmic brush with a celestial relic, provided an unprecedented opportunity to study Phoebe in detail. Cassini's suite of instruments, equipped to probe the secrets of distant worlds, sprang into action, capturing high-resolution images and collecting a wealth of data. Cassini's encounter with Phoebe was a revelation, peeling back layers of mystery that had shrouded the moon for centuries. This mission provided unprecedented insights into the enigmatic moon, transforming our understanding of its nature and history. The spacecraft's cameras, with their keen eyes, captured images of Phoebe's surface in exquisite detail, revealing a world sculpted by billions of years of impacts. These images were more detailed than any we had seen before. Craters of all sizes, from small bowl-shaped depressions to vast impact basins, pockmarked Phoebe's surface, a testament to its long and violent history. Each crater told a story of a collision that shaped the moon. The images also revealed surprising variations in brightness and color across Phoebe's surface, hinting at a complex geological past. These variations suggested different materials and ages of the surface. Some regions appeared brighter, suggesting the presence of fresh ice exposed by recent impacts. This fresh ice could provide clues about the moon's more recent history. Others were darker, perhaps coated in a layer of organic compounds or rocky material. These darker areas might indicate older, more weathered regions. These variations painted a picture of a dynamic moon, shaped by internal processes as well as external forces. Phoebe's surface is a mosaic of its tumultuous past and ongoing evolution. Cassini's instruments went beyond simply imaging Phoebe's surface. The spacecraft's spectrometers, designed to analyze the composition of distant objects, detected the presence of water ice, carbon dioxide, and other organic molecules on Phoebe's surface. These findings confirmed that Phoebe was indeed an icy body, rich in volatile compounds that had been preserved in the cold depths of space for billions of years. The detection of these compounds provided further evidence for Phoebe's origin in the distant Kuiper belt, a region beyond Neptune where icy remnants from the early solar system reside. Phoebe's composition, a chemical fingerprint of its birthplace, offered valuable clues about the conditions that prevailed in the outer solar system during its formation. As Cassini sped past Phoebe, it made another intriguing discovery. The spacecraft's instruments detected a tenuous ring of material encircling Saturn, far beyond its main ring system. This faint ring, dubbed the Phoebe ring, was too faint to be seen from Earth, but Cassini's sensitive instruments were able to discern its presence. Scientists believe that the Phoebe ring is composed of dust and ice particles blasted off Phoebe's surface by micrometeoroid impacts. These particles, trapped by Saturn's gravity, spread out into a vast, tenuous disk. The discovery of the Phoebe ring provided further evidence of the moon's influence on its surroundings and highlighted the dynamic interplay between moons, rings, and the space environment. Phoebe stands as a distant sentinel, a silent observer in the vast expanse of space, its dark surface reflecting not sunlight, but the enigmatic shadows of the universe and the profound mysteries of our cosmic origins waiting to be unraveled. This tiny moon, a captive of Saturn's immense gravity, offers a glimpse into the early solar system's chaotic beginnings. Its retrograde orbit, ancient craters and mysterious surface, and dark, icy composition whisper tales of a journey from the distant Kuiper belt, a region on the edge of our solar system, where icy remnants from the planet-forming era still reside, untouched and ancient. Phoebe's story reminds us that exploration is about more than just distances traveled. It's about the expansion of our understanding and the quest for knowledge that drives humanity forward. Each mission, each image, each discovery, each data point collected brings us closer to comprehending the intricate workings of our universe and our place within it. As we continue to explore our cosmic neighborhood, venturing further into the unknown, we can be certain that celestial bodies like Phoebe will continue to challenge our assumptions, ignite our curiosity, and inspire future generations, illuminating the vast cosmic tapestry of which we are a part, and revealing the secrets of the universe.